Well, good morning, everyone. We're going to continue on with our lectures about fossil fuels. Where we left off in the last class is continuing on with how to recover oil and the role of oil and gas in the energy landscape of the United States. What we talked about last was the fact that today most of the primary recovery of oil, which can only get about 25 to 30% of the oil out of a given reservoir, has actually been completed. I introduced the idea of a pyramid where that is basically, you can think of it as increasing with depth. That as you go deeper and deeper in the Earth's surface, up to a certain point, at least within sedimentary basins, the amount or the volumes of oil and gas that can be recovered increases. As a result, most of the shallow parts of that pyramid, the top of the pyramid, relatively small volumes. They can be things that can be found by seeps and by oil slicks, salt water wells. Most of them have been recovered by this point and really just aren't relevant anymore. Obviously, the history of the last few hundred years, or I should say about 100 years, has been that we went deeper and deeper, drilled wells, attacked conventional reservoirs, into the sort of traps and seals that we introduced very briefly here, just to get you a sense of the terminology. Um, and that for most of the last basically 3 to 4 decades in the United States, it's been a large focus on enhanced oil recovery. This can have two forms. One is that you can go to an area where somebody's already done the primary production and go back and flood water or CO2. That's very common in West Texas nowadays. And also now it's pretty common to actually do primary production, and then while you're on site, go right into enhanced oil recovery with CO2 or water flooding or steam injection, even for that matter. And that can often produce the next third of the oil and gas, such to the point where you can with water recovery or even multiple types of enhanced recovery. Sometimes there'll be primary recovery, water recovery, and then CO2 is a tertiary recovery, which can get a good amount of the oil out, but successive steps, often which the enhanced recovery makes up a considerable portion. So in all cases, though, this requires there to be some sort of mechanical pump or pressure pump, vacuum pump, whatever on the on the well that's actually producing that oil. Really, where we left off was talking about the relative amount of oil that can be produced by these conventional mechanisms, or the conventional wells. Up through about 2005, almost all the oil was in this scenario. A lot of discussion in the United States at that time was the fact that American oil industry was largely dead or was working in other places, mainly in the Middle East, moving into areas like South America, Africa, and there's even talk about Arctic drilling. Anwar Arctic drilling was a big political issue at the turn of the last century. Of course, as you all know and have basically lived through, that's changed a lot in light of unconventional oil and gas development. So before we move on, I'm going to talk about some of the other unconventional oil plays before we get into that a bit more detail. One of the more controversial ones, one of the areas that's on the horizon for people to consider moving forward, is tar sands. So this is an area, the Athabasca Basin in Alberta, Canada, is one of the main areas. Tar sands are rocks that are impregnated with tar, oil, asphalt, and other petroleum products. They're organic rich. You can almost think of these as the peat equivalent of oil. They haven't actually matured to the level where that's been converted to efficient oil and can be produced by regular drilling needs. Problem here is that the proto oil, if you will, is very viscous, or even a low from material is very viscous. As a result, you actually have to mine the oil rather than pump it to the surface. And typically, what happens in this area is just a surface mining event. Just like we talked about with coal mining and surface mountaintop removal. This is mined, trucked out to some area, and often there's locally a refinery which looks an awful lot like a smelter plant that will increase the thermal maturity and actually drive exactly the refined oil products they want. The advantage, of course, is that you can actually heat it up the right conditions and generate what you're looking for, at least to generate to the right type of crude that can be shipped typically to more sophisticated refineries to do the sort of final tuning. For those of you who remember the ongoing but certainly very controversial oil pipeline, Keystone Pipeline that was talked about from Canada down to the Gulf Coast, this tar sands, which can be mined, can be partially refined to the right type of crude. That was the main reason they were interested in building that Keystone Pipeline, because this could be shipped to the Gulf Coast area of the United States, which had the right type of refiners to refine this oil. Importantly, tar sands, it's a relevant operation at $100 barrel oil. Right now, we're well below that. We've been bouncing around half of that for most last few years. And as a result, you haven't heard as much about the tar sands recently. Just get your perspective here. The tar sands are all up here, the Athabasca Basin, Cold Lake, and the Peace River oil sands. These are all very shallowly buried, so not a lot of subsequent burial. Low thermal maturity means that sort of like a peat type scenario that didn't get heated up very much, and as a result of that, you don't actually see the oil being generated, the right type of oil to be pumped out of the ground. So the importance of this, though, is the tar sands actually contains very large deposits of oil. Canada has a very large amount of them, largely related to the it's called the Western Canadian Sedimentary Basin by the mountain building events over here in British Columbia, the shallow, deeply buried foreland basins, we'd call it. For perspective, this covers about 78,000 square kilometers. It's an incredibly big area. And it's thought to be a reserve of 300 billion barrels of oil that might be recovered. Approximately half which can be recovered economically today, and another half which they're expected to be economical as prices of oil increase over time. The point is this is equivalent to about 1 billion barrels of oil per day, although it might need to be transported largely to the Gulf Coast to be refined for the right purposes. There's also ideas about the fact that if it's not going to be gone through the Keystone Pipeline, it could be brought out to British Columbia and piped to someplace like China or something like that for refining, or even to one of the other refineries via water, marine transport. So, as a result of all this, the U.S. imports more oil from Canada than any other country. That's actually down quite a lot, actually. And, half of this net oil that we get from Canada now comes from the tar sands. This number continues to drop. And right now, if you're looking at today, tar sands, given the price point, isn't producing as much oil as it had in the past. So why do we care so much about this? Well, for starters, for example, why do we care so much about this in terms of the environmental concerns? For starters, this looks very much like all the trappings of a mountaintop removal scenario. This is an area where you're uncovering the material. The organic rich rocks tend to be very sulfur and nitrogen rich. As a result, they have the potential to produce acid rain, acid runoff. There's all the aspects of mining, such as dust and pollution. Surface overland flow of this actually can cause major contamination of the Athabasca River. But actually, one of the major concerns to this is going to be the fact that there has to be a low level of refining in many of the areas to actually heat the rock up to make it heat the ore up to the point where it can actually make crude that can be shipped in a pipeline or in traditional mechanisms. And that often leads to the production of incredibly large volumes of sulfur, often in yellow bricks, sulfurs that are stacked in the area that's removed by early heating. So, the key things here, just like mining, it disturbs very large areas. 2 tons of oil sands are needed per barrel of oil. So you're moving an awful lot of ore, if you will, in order to get a resource that's going to be worth today, $50 some. Obviously, that's why the break point even points about $100 per barrel. Per volume of oil, this is one of the most water consumptive mechanisms, 2.5 to 4 units of water per volume of oil. So you're both consuming water from the Athabasca as well as, when that water is going to be released partly back into the environment. But in perspective, Canada oil sands uses about 350 million cubic meters of water annually. Luckily for Canada, it's not a very large population, and in fact, it has a pretty good abundance of water resources. So, from a water supply perspective, it's not their biggest concern, but certainly it's a concern for the downstream water, water quality damages and things like that. As a result of the activities in the area already, much of the water, surface waters, groundwaters have become contaminated, and are, in fact, just like the sludge ponds and the sludge dams, most of that contaminated water is stored in tailing ponds. This, of course, can recharge into the subsurface and discharge into streams and lakes and in the groundwater supply in general. Just like the mining operation we talked about in Montana, migratory birds are major movers in this area. They're looking for water. They land where they can, and as a result, migratory and indigenous birds can often, consume the water, and there are reports of major health concerns for the waterfowl and migratory birds in the region. Um, and also, uh, the other aspect is sort of less important than most of the things, probably, but it's a very remote location. As a result, there's a really high cost of extraction, uh, um, removing the resource, getting it to market, getting people there, getting supplies there, and it's really just a pretty unsustainable way to actually get everything aligned to make this work. But the tar sands is an area where, if you've seen the controversy about around shale gas and like that, which we'll talk about here in a minute, tar sands is in sort of one of these end members where people, um, felt pretty strongly that this is a bridge too far in terms of how much contamination was coming out in order to actually achieve oil recovery. One of the things, in addition to the price of oil, and one of the things that caused the price of oil to drop so precipitously that made tar sands not economical was actually the access of natural gas and oil by unconventional oil and gas development. So what we call shale gas or shale oil, or just simply the fact that we can take natural gas and use it as an alternative to oil, offsetting. Oil is almost not used for um, power generation outside of gasoline anymore at all. Very seldom used in power plants. And as I mentioned in the last lecture, now there's major efforts to use things like ethane to make ethane crackers and make the plastic feedstocks we need rather than actually refine them from oil. So I think the future looks like it's moving towards natural gas. There's a lot of reasons for that, right? For starters, natural gas is abundant. There's a lot of new sources of it that have come online. There's coal bed methane in the western United States, in the central plains, in the mid-continent areas like the Illinois Basin and Appalachian Basin. Coal bed methane has come on in the last 20 years pretty rampantly. Um, just like the oil and gas and the coal, the methane is associated with organic matter on the surface of coal particles or on the surface of shales. It can be produced by microbes that interact with that coal, or it can be produced by heating up the coal or the shales and generating natural gas by increasing heat, but also partly pressure. For perspective, simply coal bed methane reservoirs, these little shallow coal seams that haven't been mined yet, where you can sink well into the coal and produce gas off of the coal by letting microbes do their thing, contain enough gas for 5 years of gas production in the United States alone. And compared to a lot of the deep unconventional wells we'll talk about in a minute, these coal bed methane wells are generally shallow, really easy to drill. I know of wells that drilled in Illinois Basin out here in Indiana, Illinois, to the west of us, that are drilled to 500-600 feet for something in the order of $50,000-$60,000 and produce $30,000 of methane a year per well, right? So there's an economic model where it's a much lower risk on the front end and a much more easy point of entry for a lot of oil and gas well operators. And we'll get to black shales here in a moment. In addition, I want to make you aware of some of the other sources of natural gas. If we're going to this natural gas economy, which many feel we are, coal bed methane is a good, clean burning, relatively speaking, a good, clean burning source of methane. Not a lot of sulfur, not a lot of NOx. If you're going to do a fossil fuel, there's a lot of advantages. This the high BTU per carbon molecule, and not a lot of associated constituents. Shale gas, I'll get back to in a second. And at least in my opinion, there are some advantages as a fossil fuel compared to coal, but there's also the CO2 aspect that's not going to go away with any of these fossil fuel options. Another source of natural gas that people talk about a lot is methane hydrates, a major potential source of gas in the future. It's actually one of the largest reservoirs of methane and carbon in the earth that actually exists on the coastlines and in the Arctic. If you haven't heard of hydrates before, it's a white ice-like material composed of molecules of methane gas surrounded by frozen water that have these sort of solid structures. I'll show you a picture in a second, I think. Similar to the other forms, the methane is formed by digestion of organic matter by bacteria and sediments, and these store huge amounts of carbon. In fact, more than twice the carbon can be known in all other coal, oil, and natural gas deposits on Earth, in marine settings, in lake environments, and in the Arctic. Despite the incredibly vast nature of these hydrates, these hydrate structures, there's still a lot of uncertainty as to where we can find them in concentrated form. What's the best way to get them out without actually destabilizing, marine environments and other areas? And there's a lot of concern, particularly on the climate side, that the ongoing destabilization of the ice cores might in fact volatilize methane by melting these ice-like molecules. The big topic, however, though, is I think you probably all are aware of in natural gas over the last several decades, is the topic of shale gas development. This has been the event of this century that's totally changed the direction. It's what has been powerful enough to remove coal as a major energy source. Not remove, but reduce, I should say, coal as a major energy source. It has incredibly vast potential. The Marcellus Shale here alone, uh, in the Appalachian Basin with the Utica and the Marcellus, are enough natural gas to reliably provide methane, for fossil fuel use at current consumption rates, assuming we go down that path, assuming we don't develop other resources. Based on current consumption rates, with 7.5 billion people on the planet, it can provide something like 1,000 years of energy for society, right? That's and as we talked about, energy demands are going to continue to increase. Per capita energy use is going to continue to increase, um, and we're going to have a population that continues to increase. If I did say that already, but the point here is that no one's expecting to try to. No one's strategy, I don't think, is to try to burn this the next 1,000 years. But it's basically unleashed a incredibly large reservoir of natural gas that really was inaccessible before because of the low porosity and low permeability, those fundamentals of fluid flow we talked about earlier in the semester. These rocks tend to have very low porosity, very low permeability, and as a result, trap a lot of the natural gas in the rock itself. If you combine U.S. and Canadian shale gas reservoirs, you're talking thousands of years of gas, easily for the North America and for really most of the rest of the world. That being said, there are countless other basins around the world that have the right geology, shales, of the right organic carbon and thermal maturity that can actually allow us to envision this being extrapolated to other locations. I worked a lot in shale gas in North America, all over, looking at the environmental impacts of shale gas and helping refine methods to get it out with less pollution and more efficiently. I worked a lot in South America, the Karoo, a little bit in Europe, and actually now in England and Ireland, and then also all over Australia and China on shale gas resources. And the bottom line is this is of great relevance. This is great interest to a lot of locations because it's great relevance to sort of find a way to meet the energy demands. Everybody, I think, has the goal of making it more efficient and mindful. I think most are mindful, at least, of greenhouse gas emissions. But based on all the different things you talk about with coal, there still are many issues with this. We're going to talk about them. I worked on these a lot. It's actually one of my most active areas of research. But I think a lot of people feel it's still an improvement over all the aspects of coal mining we talked about earlier. I think these days this slide is probably a little bit something everybody's seen at this point. But the bottom line is, the idea is that we used to sink wells into the ground in this sort of range, do conventional wells. We got to doing conventional wells that were vertical and deeper. Now, of course, the breakthrough in technology is actually directional drilling, the ability to turn the well. Of course, this is exaggerated scale. This is much more slowly ramping out than this sort of hard 90 degrees we show. So the directional drilling was actually the most important aspect. The hydrofracking component, which is basically just increasing the pressure of fluids inside of that well to fracture the rock and release, create porosity and permeability to release the oil, or more commonly natural gas, preferably oil for most of the producers because it's a better price point, but commonly natural gas from the shale gas reservoirs. So there are I put this up here. This actually was on the slide. I didn't add this to this. It says here there have been no confirmed cases of groundwater contamination from hydraulic fracturing itself in the at least 2 million wells fracked over the last 65 plus years. Of course, that's probably a little bit of propaganda in it. I will be totally transparent. There was been horizontal drilling, and is relatively newer than that. And hydraulic fracturing itself has been around for a lot longer. I think even than 65 years. I think they're cutting the argument short a little bit there. But the point I'd like to make here is that while that is all true, the brass tacks of this is the fact that it hasn't been done on this scale. It hasn't been on the vast number of wells on this deep vertical and long lateral scales, and honestly at the pressures. And as a result, there was still a lot of controversy as to whether the design of these wells and the geology and hydrogeology of these areas could actually keep everything intact. By and large, I think the industry is very well intended, has actually done a really good job. But how do they do this? Well, the typically important things to point out here is they drill a well. That well is actually, we can think of it as a borehole. It's a hole in the rock. And what's typically done is they insert a casing inside of that borehole. and then pump cement back up through the casing itself in order to minimize the possibility of oil, or sorry, of natural gas or oil getting out a lot around the pipe and into the subsurface or into the aquifer or into the surface waters. But most importantly, what they're also trying to do, or perhaps not most, perhaps it's also importantly, is they're trying to prevent fracking fluids and other chemicals from getting out as well. Commonly, this is done by doing various casings and annulus cements. Annulus is the spacing between the casing and the rock, and oftentimes this is done to basically minimize the amount of potential for contamination. So they'll drill a wide borehole at the top. That wide borehole will be cased. Oftentimes it's called spudding. Fill the area around a cement, and then there's a technique called coil stocking, where they drill through the cement that's in place, and then drill down further, put another casing, another cement, fill that in, and they basically are inserting smaller and smaller casing, in the side of cement, down further and further. The idea that the only thing you can get out of the well borehole itself would be their fracking increases in pressure and often explosives, and then the oil and gas that can come in and be recovered, as well as the water pumping in the system. So almost all of this is done by maximizing the contact with the shale reservoir along the well, allowing the gas, generating process permeability, and maintaining it by putting proppants, things like that, in to keep the rock from closing on itself, allowing oil and gas to be recovered, and also recovering the water and wastewater, produced water, back to the surface. So what are the key things here? What are the things we're concerned about? Well, most of the concerns came from concerns that there would be spills of fracking fluids, biocides, and other chemicals near the surface. Okay, people focused on the fact this is going to be put in the well, drilled at great depths, and then fractured. And the reality is, there is, in my opinion, I would agree with this statement pretty largely, pretty well. There's a very limited possibility of those chemicals migrating from depth up to the water resources or anything, water quality that's anything close to what we'd be drinking. I do think there is a concern on the hydraulic fracking fluids, which is, I think, obvious, and it's not unique to hydrofracking, is that people can actually, whenever there's an industrial process, people can have accidents. They can spill stuff at the surface. This can get into water supplies. This can get into surface water. And shale gas development, hydraulic fracturing is no different than any other industry. Accidents can happen. In reality, I think there's a good amount of redundancy in place, and I think that there are clearly documented episodes of spills, accidental spills, but they're not really tied to the hydrofracking process. Some of the other concerns are the fact that you're going to frack, down here, and you're going to liberate, oil and gas, and that is going to migrate, boil, and pollute your water. This is one where there's a lot of controversy around fugitive methane or fugitive natural gas. I've written many papers on this. I'm probably considered somewhat of an expert on that, and we'll come back to that. But I think actually, in general, few of those cases have to do with fracking going bad as much as problems with the well casing or the well annulus causing leaks or allowing leaks around the borehole where we're trying to prevent. By and large, the biggest concern I think there is with hydraulic fracturing is the incredible volumes of water that are going to flow back and have to be handled at the surface. You're talking about 4 to 7 million gallons of water per well. That's not just your fresh drinking water you give to you put on your crops or anything like that. It's often extremely salty, maybe the Marcellus up to 7 to 10 times the salinity of or even more of seawater. It's not potable. It's corrosive. It often contains relatively high levels of heavy metals, and as a result, it's not really something that can be handled terribly easily without a lot of care. So, what do we do with that? That's an open question. Ohio is, if you're looking at this from the Ohio perspective, it's of great importance to us in our economy because of the fact that that waste product is often brought to our state and put into disposal wells, up near Youngstown and along the Pennsylvania border, where people bring the water over from PA, where they're not allowed to do it by disposal, pump it in the ground, and we just get it buried deeply enough we don't have to deal with it anymore. It's not a bad strategy. However, if you overpressure that, you can actually cause some minor amounts of induced seismicity, like we talked about earlier in the semester. So, there's always this possibility that some of this stuff will get spilled onto the surface by accidents. Intentional releases are controversial and maybe thought to occur at least by accident, maybe intentionally in some locations. but there's a major economic and environmental concerns with how you handle the wastewater from this kind of things. So people have talked about the dangers in a lot of different ways. In terms of contamination of the aquifers, contamination of well water, fractures being generated that can be released. I think most of it is actually pretty overblown. I think the industry is pretty well regulated actually, um, and there's a lot of people whose job it is to watch and make sure, trust but verify, make sure these problems aren't getting out. Most of the problems have been surface down, people spilling things accidentally getting into the aquifer, or it's problems with this vertical borehole. I'm not dismissing the importance of that. In fact, I routinely actually work as an expert witness for people who have methane contamination in their water wells. But what I want to highlight for you here to recognize is that the only thing that differs is the pressures of gas they're accessing below. In many cases, those same boreholes, those same casings, and those same cement would be there if it was a conventional well or an unconventional well. It's just that the rate of activity is increasing, and I think, as much as anything, the rate of the activity has increased, which means you have more people with less experience drilling wells. I think that's part of the issue. The other thing I'll say is that since the time I started working this to now, you see the laws have changed around casings and cementation, how deep it has to be. And I think the industry has had to respond to increasing oversight and regulation that made the process, um, more robust as we went along. So I'm not trying to be political about it, but I think it's a situation where there is really middle ground between the two end members of the arguments. Um, a big concern, however, though, is the amount of water that has to go in for fracking, right? So if you have to put 4 to 7 million gallons of water in, the water has to come from somewhere. If you're in Ohio, it rains here enough, we probably don't really care if they use, develop water well, use that water supply for that with areas, at least in most years. But if you're in, West Texas, you're in New Mexico, these are areas that have been long-term drought, where water resources are, quite frankly, really, really stressed. And as a result, there are areas where there's more water being used than there is water, for fracking, than there is needed on a regional basis for other industries, agriculture, and human consumption. Um, as a result, if you look at the impacts of ranches in West Texas, many of them have sold for more money for their water rights than they have for the energy rights, because of the fact that certain areas can produce enough water to actually lead to production. Be used for hydrofracking areas. The other concern, though, with these ponds is not just having water to go down. These are actually usually retention ponds. So that water that comes up, the produced water, it has to go somewhere. When that water comes back up, again, something needs to be done with it. And quite commonly, that water is put in a retention pond. Some of it is allowed to evaporate. They're usually clay-lined layers and have actual plastic liners, prevent that from leaking out. But of course, there can be tears, there can be minor leaks, and there's a possibility of some problems with this. Eventually, this stuff is pumped out, usually when it's more concentrated, to remove the amount of mass material that has to be dealt with, and basically brought to places like Ohio, or in New York, it's often spread on the roads to control dust. And in many cases, in Pennsylvania, what they try to do is actually tie it to local municipal water sewage treatment systems, to put up a new sewage treatment area. The problem is the needs for municipal waste treatment and the needs for treatment of these types of brines aren't really the same. And there are many documented cases that didn't really work out particularly well. Obviously, you can see how complex these operations are. There's obviously a possibility for one little thing to be wrong somewhere along there. I think the industry has done a pretty good job of trying, and I think there's a lot of regulations in place to make it safe. By and large, it still has problems. It still can be leaks. The most common one I'll bring your attention to here, the one I worked on the most, is this issue of methane in groundwater. When they started drilling wells, there's people who immediately started reporting, I had this gurgling, my pipes started shaking, I lit a match and my water burns. There's foul smells, there's bad taste in my water. And the reality is this became a really big controversy for a few years, for a decade, and became a major area of my research. I worked in this for almost a full decade. The arguments on one hand and the other hand, always a two-handed scientist. But on one hand, the argument is that there's always been methane and then there are hills, right? My granddad used to talk about drilling wells and hitting methane, right? That's absolutely true. In most petroleum basins, as I mentioned earlier, the top of that pyramid is we look for areas where there are natural seeps, where there's salt, where there was oil, and we drilled wells in those locations because of the fact there was evidence of methane there. So there is, in fact, an argument to be made that there's naturally occurring methane in a large number of wells. And many other workers have shown similar results to what we did, which demonstrates there is massive amounts of methane in groundwater across the Appalachian region and other sedimentary basins. On the other hand, many would argue, I used to have good water here. I had no methane, I had no salinity, and I had good taste. And I had that well for 60 years. And then company X drilled a well, across the street, and then I started having problems. And the reality is, I feel pretty comfortable in saying at this point that there's a small subset of cases where that argument is true. There have been accidental releases, of oil, of gas, particularly. And I highlight for you again, the more common concern here is whether the annulus cement and the metal casing are actually adequately retained and don't allow any of the gas to be released from those areas. So, our job effectively was to determine what the truth was here, and we did a lot of research in this. And I to highlight again here, what we found is that most commonly the problem was related to actually problems of well integrity. These casings sound fantastic and great, but they're obviously stainless. They're obviously just they're steel casings in the end. They can corrode. They can undergo embrittlement. They can crack by being torqued and bent in the subsurface. They are designed to be these beautiful. I mean, just look at this diagram. Look how perfect everything is, concentric and in place, and it's so orderly and engineered, and everything's gonna be fine. And that's true. That's true in many cases, I'm sure. But there's also other examples where the borehole deviates, where they don't get the things placed where they want to, where there's not a concentric casings around all sides of this. This is an example from Canada. They've actually exhumed the well casing. This is obviously pretty close to the top of the well where they could actually dig this thing out. But just look how poorly concentric this was here. Imagine how hard that is to improve as you go to multiple meters and kilometers of depth and around directional drilling, so like that. The other component here is that the casings have a very important purpose, and I think they actually fail in the minority of cases. What does, I believe, at least in the data, have much more of a common aspect here is that the well annulus, the space between either the casing and the borehole, the rock wall in the borehole, or even the space between the two multiple successive casings, has to get filled by something, cement. So here's the issue. Fundamentally, no matter how you want to spin it, here's the issue. You pour cement in. Cement's designed to fill a space. Cement's designed to make sure no oil and gas gets around. I don't know how many of you have actually poured cement in your life. I've done it a handful of times, but the most important thing to recognize is when cement solidifies, it contracts. And a consolidation of the cement actually leads to the material it contracts here. There has to be some expansion someplace else, and you see these radial crack expansions all out through the cements. And those fractures can actually, if they're connected, or if in fact the cement just didn't get into an area, this just fell out afterwards. But there's also times where it's not clear when you have deviations of the borehole that you're getting cement uniformly around the casing itself. Those fractures, or just an absence of cement, or quite frankly, in the early days of this, where there was no regulation that said you had to put a casing or cement into the depths that they were of concern, this is what I believe is the issue where most people have run into problems. Imagine you drill a well to 1,000 feet. You're required to put a casing and cement annulus in this cement in the annulus to 1,000 feet, and you hit a gas pocket at 1,200 feet. That gas is going to come up. You drill down further, you hit a gas pocket, that is going to come up. The annulus cement may stop it, but if it migrates on the outside of this casing, and where there's another round of annulus cement out here, and that's not fully solidified, or there's fractures in that, or there's spacing between those areas, that'll actually migrate up and around that quite easily. I imagine many can see pathways. So at any rate, I think that this doesn't mean people are necessarily evil. Doesn't mean they're not trying, but it does mean we have to recognize there's imperfections. Our research, just to give you a sense of this, our research showed, I think I might have said this earlier in the semester, that about 6% of wells we estimated, maybe even less, experienced some amount of contamination. We were pretty heavily vilified for that stance, but the industry, oil service providing companies, Schlumberger's internal documents actually use the number like 20%. suggesting that they were saying, hey, you should use our products because we know this leaking occurs much more frequently than we actually identified. Apologize here. Apparently, my slide on hydrates is a bit out of order. But this is to give you a picture of those hydrates that I was talking about earlier. These sort of ice-filled bubbles, or sorry, ice-like, structures that hold these methane bubbles inside. Here's some that have actually popped open as the pressure's been released here. They're pretty cool. Gulf of Mexico and many other near shore environments are commonly used to look at these. One of the last things I want to highlight about the fossil fuels here that's actually far far underappreciated is actually the equivalent to the impacts of exploration and development to coal and oil. So we tend to talk about things like methane leaks. They get a lot of publicity. People's homes, having methane, burning in their sinks, that gets people's attention. But there's also other aspects of oil and gas exploration, development, and delivery that cause some environmental concerns. We all, saw the things like the Exxon Valdez. We all saw the Macondo Bay aspect in the Gulf of Mexico that got brought oil to the coastlines. We've sort of forgotten about the fact that some of these major pipelines we have to bring oil and gas around actually disrupt migratory patterns for caribou, things like that. So, by and large, I worked for almost a decade exploring the water quality and energy aspects of shale gas development. And in the end, when you go out and talk to people, the impacts that they're concerned about, that impact their lives the most, are usually the fact that somebody built new roads in all over the place in the area to get equipment around. People put in supply lines. People put in pipelines. They devegetated or deforested areas to put in pipelines to get materials to market. They basically changed the landscape. They changed the terrascape of the area in order to complete the pad. The pad itself is, can be small to pretty large. So 20 to 80 acres is not at all out of the range. That's a pretty big area for a lot of people. If you're a farmer and that comes into your field, that can change your crop cycle for a year or two. If you're somebody who has land for recreational purposes, hunting or something like that, that can change everything for you, right? So the punchline is this is a factor that actually, impacts the ecosystems of these areas in pretty major ways. In theory, as long as it's done well and successfully, and there aren't any problems, it's typically going to be a short-term impact that vegetation can come back, you can plant second year later, whatever the case may be. There's no spills, no major leaks. The reduction of these wells can be, and I should have shown you a picture of this. The footprint of this well, 18 months out, is often something that's significantly smaller than a small garage. Or in many cases, it's an area where if they didn't keep it cleared out, so nobody bumped into it, you may not even notice it in a farmer's field. Okay, but there are also some impacts of setting up this exploration aspect that can have major impacts, right? So there's a lot of controversy around drilling in the Arctic, where we could destabilize things like hydrates in the ice cores. We could permanently change environments where quite frankly, are some of the most endangered species live. Okay, there's other issues where we just don't have a very good solution yet. What do we do with this wastewater disposal? We can't just dump it into the rivers and let it mix out. It can permanently damage the rivers. We can't just put it all into disposal wells, or else we have to drill a lot more of them, and we have to worry about things like seismicity and stuff like that, microseismicity. And there's concerns where it's not entirely clear how we're gonna deal with that, right? The other component, of course, is that we have to recognize all the fossil fuels contribute to greenhouse gas emissions, and we'll talk about that more as we go along. But by and large, it's sort of it's often is the accidental releases. It's the known unknown. We know there's a chance of accidents. We don't know what they can be. We don't know how bad they can get. We don't know how someone's going to respond. As a result, there are examples such as the Deepwater Horizon and the Macondo in Gulf of Mexico back in 2010 that are accidents that in hindsight we see all the problems of more regulation and more oversight that would have helped, but where things can get out of hand really quickly. So just to give you a sense, I mean, imagine working on a rig out in this is the Kulik drill rig in the Arctic. Just look at the shorelines, look at the conditions, look at how violent the water is. you get the sense there's always the possibility for things to go wrong, um, and quite a lot of concern here. Shell has actually bought leases for portions of the Beaufort and Chukchi Seas in the U.S. and the Arctic Ocean. Um, there's a reason they're doing that. There's estimated to be about 27 billion barrels of recoverable oil and 130 trillion cubic feet of natural gas. Um, for perspective, that's about 30. That there are more than 30 times the annual annual imports to the U.S. from OPEC countries. So being able to produce that in Canada or even in some U.S. land holdings in off Alaska has obvious geopolitical implications, economic implications. There's a reason people think about doing this, but when you start thinking about the problems, just recognize the possibility of something going wrong in this picture. Look how rough the seas are. Also, I mean, how are you actually going to get this oil and gas to market? 27 billion barrels of oil. People will build a pipeline for. People will find a passage to get ships out. Okay, there can and eventually will be for accidents, but gas pipelines, you can't really just put that on a barge and carry it somewhere, right? How are you going to get that out? So that the locations of major concern. So some of the big problems I want to highlight here with expanding to the Arctic areas, there's very little infrastructure. There's no deep water ports. There's no safe harbors, if you will. There's no airports. There's no housing for the workers. Everyone has to be housed on these rigs. Everyone has to get there. There's gonna be problems that are gonna occur. It's too cold to drill most of the year. In fact, the drilling season is short enough that the exploration season is about 3 months of the summer. That's a lot of pressure to do a lot of work in a very short period of time. Often extreme weather events, tides, winds that can cause unexpected issues. There's obviously from an industry perspective, there's been a ramp up of regulations after the Deepwater Horizon. That was a very visible problem that caused a lot of issues that made people pay very close attention. There's been as I'm sure you probably have known, there's been a abundance of lawsuits and activities by environmental groups, conservation groups to prevent this from happening, which of course changes the price point for industry a lot. But by and large, the reason this started out, this was ready to go in about 2000, early 2000s, mid 2000s. People were going in this direction, even as recently as maybe 2010. But the bottom line is the economic crisis of 2008 brought oil prices down quite a bit from the $130, $150 barrel oil that we were dealing with in the early to mid 2000s. And then also the advent of shale gas development, allowing there to be more oil and gas extracted from unconventional shales, brought more oil and gas to market and dropped the price point down. And we were living through a time now where oil is, there's always economic cost of the greenhouse gas emissions, but the price of actually getting oil and gas out of the ground from shale gas is even driving shale gas operators out of the market. It's getting so cheap. As a result, the biggest problem is that there's uncertain economics. You can't predict 5 more years, maybe something will go wrong with shale gas, and we'll be getting back to $120 barrel of oil. But for now, it's not economic, and it's hard to really try to build all this infrastructure around something you don't know if it's going to be there. There'll be a demand for. So I think for now, Arctic exploration is sort of slowed down at least. But notably, Shell spent hundreds of millions of dollars on the Arctic before halting operations relatively recently, and now, in fact, they've actually moved a lot of their corporate directions into other sources of oil where are more sustainable. So this is actually the rig, big transport of South Korea, where I think, if I remember correctly, it's supposed to be used to look for hydrates in that area. Has limited other energy supplies. The biggest, or not the biggest, but one of the biggest aspects of oil and gas industry that gets overlooked in terms of its impact is the pipeline controversies. Not just controversies, but the pipeline concerns. Right. The Keystone Pipeline is an example of this. This came about in maybe about 2010. People wanted to basically transmit these pipelines from use these pipelines to transmit oil from the crude from the Alberta tar sands. Multiple pathways were basically thought of. Some to bring it over to the or refinery capacity in Illinois, some down to refining capacity through Oklahoma, Kansas, and Houston. But the whole reason there was a drive to try to push this to this part of the world was the refining capacity around the refineries that can handle high sulfur and very viscous oil. And that's actually quite a challenge. The price of building a new refinery up here is almost insurmountable. It needs to be an area where the refined product can be brought to market easily. And as a result, there's a desire from both an economic perspective and just a what kind of stuff can it refine perspective to get this material to the Gulf Coast. So the idea here is that pipelines would transport oil um, from Canada to refineries in the Midwest and southern United States. Uh, the controversies around this are are pretty profound from an environmental perspective. Pipelines don't have the best history of not being environmental problems, right? There's often spills and leaks from pipelines. There are 14 spills since 2010 in the area that have impacted water resources, some near Yellowstone and things like that, through Native American tribal lands. And then there's also concern if we go through this big effort in the U.S. Is this even going to benefit the U.S. consumer, or is this actually going to be going to exports, globally? The reality is that it's going to go to the exports where there's the best economic outcome for doing so. So there are major concerns about encouraging use of tar sands as well, just because of the fact that this was almost going to one of the dirtiest forms of carbon energy that we'd really consider developing at this point in time. So all the above sort of led to this largely being slowed down, and basically there's thought the pipeline would encourage development of these resources even with really poor really poor economic prospects and poor environmental issues. So that there's a desire for people to push back on this and prevent it. On the positive side, the American consumer, many folks would agree that there's a value of preventing imports of heavy oil, particularly in some cases from countries that are not our allies. In many cases where there's countries where it sort of props up controversial dictators, so that there's always a desire to have energy security. Most people would agree that pipelines are safer than transporting oil via truck or rail or cars. Um, but in reality, pipelines themselves have many issues. We'll talk about here in a second. And basically, by 2015, TransCanada pulled its permit and basically put the pipeline in a state of limbo. And I think that basically doubt that you'll see it changing. Although realistically, this decision had much to do with the price of oil as it did to the environmental impact or pushback, I should say. And then it was officially denied anyway by the State Department shortly thereafter on November 6th. So, let's talk about oil pipelines a bit here. How are we doing? Let's talk about oil pipelines a bit here. Oil pipelines, tend to be safer than trucks, but as we're going to talk about in the next lecture, that doesn't mean they're necessarily safe. They do have potential for leaks, for failures, and other problems that can cause a lot of issues. I'm going to end here for today. I'm going to pick up with pipelines, and then we'll get into our last set of lectures on mineral resources here before long. Hope everyone's doing well. Miss talking to you live. For those of you who were attending, and we'll keep going along here to get the last lectures up for you. Have a great weekend. Hopefully, if you're watching this on schedule, that means you're about to have a great Thanksgiving. If you're behind schedule, hopefully you already did.